So we were more or less here. So I try to resume. So you see, in this point of view, the basic objects are really the functional integral, these objects here. Okay, so objects like this. Okay, so we want to study this, and we have seen that we can expand. So we have seen that these are expectations. It's for expectation, then it's given by determinants. Then we have seen several kinds of problems. So first of all, so you see, I recall you that the structure is something like this. You have a sum or an integral, so of course you have to control the integral, and then you have this force field. So typically you have three kinds of problems. The combinatorial problems of the number of terms in this expectation, the fact that you want to make the integrals, and the fact that the G must be then, you must use some of the G to make the integrals, but also you have to bound the G. So you need some L1 norm for the G and infinity norm for the G. Typically, all the problems of interest, all these norms are not really finite, and then you have to do something. So then we have seen several problems. We have introduced it into expectations. So all this stuff is not regarding animation group. It's just to define because it's just a naive speed expansion. So in a sense, so take into account that a part of this formula, all the rest is not typically addressed in the physical literature. In the physical literature, people do not worry about the number of stuff. The problem is just that each of these terms is a problem. So I'm just reversing the usual presentation of this kind of thing, trying first to understand when this functional integral is not a meaning, and then we see. Assuming that this norm G1 and G3 is sense, but then the real problem just is to consider cases in which these objects are not there. If you have a gap, this G1 norm is typically fine. And if you have a lattice, then the G is infinity norm. So this is the reason why if you have a gap and if you have a lattice, you are in a sense in a much better situation because both these norms are finite. The organization group for terms you are saved by this formula we have seen. Okay, so we have seen. So this is the first possible bound. This is the bound with this factorial. We just bound the graph. Then there is this idea of the determinants, the signs. So it's a series. So the point is that this is a series in lambda, which each term is done by several terms. So if you bound the modulus of the sum with the sum of the modulus, you get 7. So that's it's done using this determinant bound. But if you use simply the determinant, you lose the connection. So at the end, if you want to use both the connection and the determinant, a possibility, there are other possibilities, is to use this formula, for instance, which tells you because you are extracting from the so it is nice to make maybe. So the loop you get, so you extract a line for each of the it's not that easy to derive. I'm still hoping that one day someone will find an easy way. So there is a proof in my book, or the original proof of bridges is 2 page, 1 page. So you have to fill all the text. But in principle, it's very easy. So it's in principle, it's everything. So it's simply interpolation form. So at the end, I'm afraid that maybe I will, if I have time, I will try to give an idea. But morally, it's essentially simple interpolation formula. So it's simply this, something like this. That from 0 to 1 of the derivative you can write an exponential is the integral plus like that. So it's simply interpolation formula. So you repeat several and several times this interpolation formula. So let me see if I can give you an idea. So for instance, you introduce a set of this x1, xr. So you have to So you introduce the function w, in which the t are such that tk if n is a connection which cross the boundary and the one otherwise. So let's see at the beginning. Okay, the idea is to separate the disconnected path. So you start from this x1 p1. So v11, what means v11 is defined here. Yes, v11 are the fields, are the propagators which connect a point in the set of points PE, PJ, and a point in the set of points PJ prime. Okay, so you see G, X, I, J, X, I prime, J prime. So you have PJ, which is PJ prime, then the G connects. So for V11, consider a propagator inside the cluster P1. So you introduce this W, then W is according to the definition before it is V11, this is the definition, plus P1 plus the rest. So you see, if you put P1 is equal to 0, you don't have anymore the connection between the cluster 1 and the rest. So because the point is that one wants to extract the connected part. So if you put Q1 equal to Q1 is equal to 1, it's B. So people take all the possible connections between J and J. So if you put Q1 equal to 0, then you are disconnected. That's 1, 2, okay. And then you use simply this formula here now, which is obvious because this is the integral of B is equal to 1 minus 0 plus 0. So this is to put. We have said that even not written. W x1 1 is B. So you start from maybe it should be You start from B, the original B. Okay, then you rewrite in this way. So it remains only e to the w x1, 1, which is simply the sum of the B. Okay? Okay, we'll define it here. Q is the sum of J prime. Okay, so you have in general this structure. Okay, you have, maybe forget the first line, which is important. This is the, you start from the simple, so the point is that you start from the expectations, which contains all the possible terms, the connected and the non-connected. Then you want to extract only the connected part. So this is the determinant. The determinant can be written this way, according to the rule. So this definition. So now you want to write the simple expectation in terms of concrete. So you want to extract the connected part. So we start from this. So now this is the simple expectation we are writing this way. So now this piece is surely disconnected because there is no anymore connection between one and the other. So this piece surely is not part of the concept. Okay. So now you have this one. Now, so what you're done, when you make the derivative, you extract the P, contains a propagator. So now we have realized the connection between one and the rest. Okay, but of course it's still not necessarily connected because you connect one with the rest, but the rest will be connected. You connected this. Now we what we do is confident because we have to iterate this idea. So if you have only two feet, it's finished. So let me say that the form is complicated in general because you have several steps. You have two steps, it's finished. So you can only do one, two, the three is a very clear thing. Only two steps is finished. Now, so we want to see what happens in general. So one repeats the same step now. So now we have this W. Then again, you want to separate so this is connected with 1 and 2, and now we want to connect it with 3. So we want to separate a piece connected with 3 with a rest. You introduce, so now you define 1K. So of course it's different because now this is an example. Let us consider 1, 2, because I'm saying this connects one with one of the other. I call one of the other 2. Now I introduce this W, x1, x2. This again, if you put all the t equal, reduces to the initial one. If you put t2 equal to 1, that is exactly equal to the previous one. That's it. This one is not true. Instead, but there are two places. 3 to 3, which are this one, then the allowed 3, which are here, function, which are rooted. These are rooted. Then the bridges 3 are rooted, but then they are rooted. Okay? So now you see, if you put T2 equal to 1, you get the previous thing. So you can do exactly the same, right? So maybe there is not a step. Now the integral of W T2 contains a piece which is disconnected and the rest. Okay. And now I write here only the piece which is disconnected, which is connected. So then there is plus something I did not write. Okay. I want to write only the non-disconnected. Of course, I say non-disconnected because they are still not connected. I don't know if they are connected. You know that the other piece is surely disconnected. Okay. So it's like here. So this is disconnected. Now I have here, so this is plus e2 x1 x2 t1 0 plus like this, but that is surely disconnected because if you put t2 equal to 0, you see 1 1. There is no connection between this and the rest. This is the no, the lines are when you make the derivative. Because when you make the derivative, you see, to make the derivative, you see 2, for instance, then you get a term which connects 2 with k. But you have two kinds of terms, or this or this. Maybe. Okay, so now I'm saying. Okay. So you see the first line is 1 and 3. And the second is 2 and 3. So when I make the derivatives, I can have, so I repeat the same argument as before. Now I have the derivative, so I keep only the connected terms. So I can have two possibilities. I have EL1 was the one before. Then I have all. Then you continue. So you have only 3 clusters, you have finished, and now you do another time. So this, I wrote the 3 and then I finished because it's more and more complicated. So do it yourself. So if you have 3, but now I want, so you see, just for joke, I wrote explicitly. So you have 1, so now is the case in which you have 4. So you have 1, 3, 2, 3, and then you have the connection. 1 can be connected with 4. 2 can be connected with 4. 3 can be connected with 4. Then the other. So if you put T3 equal to 0, this is disconnected the rest with the 4. Okay, and then you continue. Then you see, now you have, so this is the case in which you have 3 cases, and now you start. It's not so terrible. So what we have to check. So now we have now to understand that the T okay, are a certain structure just by given there, and prime is the minimum K such that L crosses exact and L is the max. So you have a structure of this T, which is important. But what is important in this way, you see, you can, it's important to say that when if you consider a finite number of clusters, then the formula is very simple, it's fine. Okay? It's just that the formula is general, is more complicated. So anyway, now you see, now what you do. Okay, now there is the point that you have to exchange the sum. So, so you okay, now maybe I can skip this. Okay, now you have to, instead of summing over x, you invert the sum of x with the t. What is important? Yeah, the crucial point is this line. Now, of course, this is with the, now we put the integral. Okay. Now we remember that the v contains the psi. Okay, the v contains the psi. So when we make the integral, by the definition of Grassmann integral, when you select, so now also very, very, very clear. When you integrate over psi, this v contains the psi. So the only non-vanishing terms you have selected, this L1 connect to phi. So when you integrate, the only time you have the psi here, but also you have the psi also here. So of course, if you have a certain psi here, that you cannot keep the same terms with the psi here because psi square is 0. Okay. So so first of all, the only term which is non, so if you remember the definition of Grassmann integral, the psi is 0. The psi is non-zero. So you have to keep the psi here, and then gives you the G, the propagator. What remains is the integral of this object, and that is a determinant that you can bound by this Riemann amount. Also, the last thing to do, the way I keep the text, otherwise it's too much, but in my book, for instance, you can check this identity. Okay, here you have some things, but you will find you have to read it a bit carefully. There is some combinatorics here telling you that the integral over this T gives you 1. Okay. Okay, then that's more or less the thing. So to repeat, the realization of the truncation, I think of the connector pattern, I think is very standard. And then at this point, we have simply to use the rules of Grassmann integral, saying you that the V on only the propagator, this remains the propagator, and what remains here is a determinant. So here you have this fraction of the V, so what remains here is the sum. So if you select a tree in the W, you cannot have the same field. That is very important. It's a very important point. I try to repeat. In this V, there are some C's. Okay? But you need to make the integral non-zero, you must keep the psi. But then you don't have any psi. All contribution from this, in which you have the same psi, disappear. Okay? So what remains here is the same as this without the psi which are in the tree. So this means that you are extracting the propagator from the psi and the rest is that's something very old, something of the 80s. It's a sort of basic of everything. But that, again, is nothing to do with the organization group. It's just some abstract properties of the expectation programming. You can write something similar. I think that's for fairness, what was done before for boson. For instance, there is the analog of this formula for St. Gordon. For St. Gordon, instead of the determinant, you have e to the minus b. Minus b is the complex combination is positive. Okay, but now in principle, this course should be about a relation group, still not interested in the relation group. Okay, so now suppose that you agree on this formula. So now let's just come back and see what we do with it. But in a sense, all this is, in a sense, is mathematics. So it does not depend on the model. It's a simple properties of the truncated expectations. What we have to do is now to apply. Yeah, okay, the GK boundary, sorry, that's exactly the point. So now the physics depends on the G. I mean, for any model you want to consider, you have a different G. And then it depends on the dimension of the radiator and stuff. So now the physics answer cannot be general. Otherwise, if you have enough result, geographic piano was, and now it was about how if you want to consider all the properties the width idea, of course, the concept of dimension, scaling dimension, and it's crucial for all the analysis. So let's start then in general. So this is Vn, and this is, let's say, in 4 dimensions, but yeah, of course the procedure will be different depending on the dimension. That's maybe I should stress. Okay, let's start. So, let's, for the easiest case is in 4 dimensions. For the ultraviolet, it's even better. So let us consider a 4-dimensional case in which this field psi is the real model was this one. Okay, this is the real model, the Z, but then I integrate the Z, and then this became simply quartic in the psi. Okay? So now the idea is to make this decomposition of the propagator. So now I use so now the point is, so this is getting to the primary PA, so this is a positive time, this is like this, which, so now in my life, So now, I, if I see that not bounded in any order, but also they are not bounded even. Okay, you will get things in. They are not. It's not possible to use them. So the idea instead is to make the integration in steps. So you decompose this measure, it's the product of the two measures, and then you integrate this, not that. Okay? Why you do this? Because this now is very well defined. This has no now GM plus one is simply so. Of course, I mean, this is still nothing because you cannot cope with the problem again. So we have to do something to continue to interact this way. Then we have to do more to do something. And when not on the last, The battle bridges formula give you no factorials, and then now we have a finite G infinity and G one no. So now we can use it. Okay, anyway, so let's do the first step. That is the first step. So now I think that everything is clear. So we have I wrote this, I replace this, I integrate, and this is the definition of integration. P index n plus 1 e to the b is the sum of the truncated expectation by definition on n plus 1. So I call this potential. This is a very is explicit, and I mean this is strange. I mean this fact that is sometimes considered mysterious that the innovation group produce non-local monomials. So it's obvious. I mean you have truncated expectation of product, even if that the starting point is local, you will get an unlock because you have to contract V in different points. So the external fields, the fields you don't contract are in different points. And here, so you start, even if you start with local, we get to local. Okay. Okay, and so now these are the Gallavotti treaties. It's convenient to represent this sum, for reason you will see, this sum here, in this way. You will see why it's convenient in a second. Now it's unclear why it is convenient. But so you have the epsilon TB represented with the form. Epsilon TB cube line. Epsilon TBVV we represent with this line. So it's just okay. So now the important point is that if you bound this V, you will see also which is the dimension. So you will get it's a very easy computation that if you make now this, if you apply the Bartlett-Bridges-Federbush to this Vn plus 1, you will get a bound gamma to 4 minus 3n divided by 2 minus n. So, So now can finally up to this point everything is completely clear, right? The point is that many usually so it is something that you got so now it is now so what is the limitation? The limitation is if there is some fact if you do the same, you will expect problems. They will increase. The other terms will decrease. What is called renormal. No, in this case, it's very simple. In this case, it's simple because we are not trying to remove the ultraviolet part, the ultraviolet loss. We are considering just the infrared. So remember when I explained yesterday the theory is good, the infrared is better than the ultraviolet. So this theory is good, the infrared is better than the ultraviolet. In particular, so now, which is the idea? Before integrating, so the idea is very simple. In this case, it's very simple because the only dangerous terms are the quadratic ones. Okay. I'm changing on our se parameters of the non-interactive theory. Non-interactive theory is the quadratic. You take a mass, you take the wave functionalization, and so on. After the first step, I put the quadratic term there, so I have to integrate respect to a theory which has different values. Different. So these are the Dressel parameters and the Bayer parameters of the old style relationship. So I simply extract the part of terms which are dangerous. And in this case, it's very easy because are quadratic. In more complicated theory, you have to study also the quartic term. But in this kind of theory, or in Latina and so on, it's much easier. So just to recapitulate, if you have, for instance, a mass, then you don't have to do anything. Because the mass is different. And you have an axis, then all these moments. Don't have the mass, you have to do it. Then the time now, and this is the property, it is not special. This is the property that is the one fact that is here, is the one like this. You want, I can see the name is that this, what is that? So now I can tell you what is the okay, maybe would be nice not to start. And that is the general structure of the tree. So the point is that when you apply this, okay, okay, maybe better it's on the tail. Well, good. I first should be there. I mean, it's just the picture of H and -1 and -2. There are two ways which you can use it. One is practicing. Are alone, no school, but good people. So, no one. They're not annoying. Then there is also Balaban, which is another. But people without school remain a bit alone. Okay. Okay. Now we use this formula we have seen. Okay. Now more or less you continue, and then okay, then now there are several details that I have to skip, of course. But at the end, what you get is that At the end, what one is really interesting. No, I show you. I mean, I'm not going just a second. Nothing to do. Okay. Something like this. This gamma mu is the 3-point function. So you have to consider the 3-point function, you make it the amputate, and then you have, okay, ask to Bianchessi there, I mean, he derived this formula. If you look at how the different books, complicated formula, but the important point is that the gamma mu is something you can copy by two groups, and then you will get, maybe I'll show you the result. So these are examples of graphs. Okay, so let's have the graph I was telling you. Because it will be the fifth order sense, and it will be class and so on. Yes, and so these are the bounds. So I think it's an exercise to be sure that, I mean, because you never know that. So you see what I prepare all this kind of. So that's the result. Then you get the A bar is the Jackian bind. So that's maybe is the main conclusion. So that's one thing. Get the conclusion for the G. People is cool. So I get A. That is the G, which is regularized, the partition cutoff, so it's equal. So that's it, you want. It's equal to the perturbation theory of Cergy and Binder of formal perturbation theory, plus correction. The correction contains a term which is small because m over n is small, the mass of the area is much smaller. A term which is small if the cutoff is much bigger than lambda, and a term which goes in the opposite direction, okay? But it's made small by this lambda. Yes, maybe, okay, it's just, no, that's, I mean, no. That is for mathematicians, but not for physics, because all the standard model is to replace this lambda over n with log lambda over n. So all the theory from Fermi to now, so in 70 years to replace, I'm not able, but in principle, people believe that theory is going to replace with the log. But at least we can put a log here in m over n, because this was 10 to minus 6, so at least this equals to 6 to the 4th. It's better 6 to the 4th than 10 to the 6th. But because the idea is that if the theory is a normalizable theory, you should put a log. So if you put a log, you are very happy because this is much smaller. You can put, for instance, but this is 1 over 37, so you can arrive up to exponential of 1. Okay, so you see, but in principle, if you can consider n small, lambda small, that is a solution of quantitative theory. So the theory is not convergent, so the sum does not exist. But still the correction is very small if you compare lambda small and lambda much larger. So that's it. So how is possible? So that is the conclusion of the question I was asking at the beginning. How is possible that a series which is divergent gives correct information? Because you have this kind of bound. So if you have parameters such that it is small, then you have. And I think in the physics we so,
yeah, thank you very much.